the outer edge of the ring has more charge than the inner edge, or the vice versa, the inner side has more charge than the outer. So what would that mean? The sigma is non-uniform. Okay. So I can give the sigma non-uniform. I can give the sigma either an increasing function of R let's say alpha R squared. So what would that mean? That would mean there isn't that much charge here, but as you go farther and farther out, there is more charge. Just kind of like the semicircular ring one that we were doing. More of the charges on the outer edge. But if I give you alpha R to the -1, alpha R to the -2, those would be decreasing. So that would mean most of the charge is on the center. And then there's less and less charge as you go out. So which of these would be if I try to find the 1 meter away, which of them would be stronger? So if you go to this one, more charges at the outer edge. But the outer edge, it kind of starts behaving like a ring then, right? So then the electric field has to come down and back up. So that one is probably going to be weaker than the plate. So if the plate was like 303, let's see here, it depends what point I'm doing. If I'm doing the point 0.354, right? The uniform plate was 303, so I'll probably expect it to be something like 250, 240, something like that. So I would expect this to be weaker than the plate, but stronger than the ring still. The ring is 138, you see, because it's truly not a ring. There's still charge here, but it's not as much charge. But if it's the other way around, where there's more charge here, then I would expect it to go really concentrated here, you know? So then it takes a longer time even to diverge. So then I would expect it to be more than 303. So if you want, let's do the decreasing one, since we haven't done one of those. More charge towards the middle, you see? So later when you're practicing rods together, you can practice rods that have decreasing function. You see, something like lambda is alpha 1 over x, 1 over absolute value of x. You know, that would be equivalent to this guy, or alpha over x squared. And that'll be similar to this guy. So more charge in the middle and less charge on the outer edge. You see, it's opposite. Okay, so then the original setup will be the same as the uniform rod. So let's look at that. It will look like this, except now the sigma will not come out of the integral. So you're going to have the 2, the pi, the k, the x, those come out. Sigma stays in the integral, and all of these stay in the integral. So let's write it down from there. Okay, so E is going to be 2 pi k x, and then sigma 0 to r, sigma, and what was the rest? Sigma dr, or sigma r dr, sigma r dr over what? Over what? Okay, let me check here. X squared plus r squared. X squared plus r squared to the 3/2. And then that's where you put your function for the sigma. Okay, so let's say it's this one, linearly decreasing function. Okay, so then what will that be? Okay, 2 pi k. So let's say I'm doing it at the point 0.354. 0 to 0.5 alpha times, and then it's going to be alpha times 1 over r, right, for the sigma. Then r dr over 0.354 squared plus r squared to the 3/2. Oh, then the r cancels. Oh, now alpha comes out of the integral. Well, so then I just integrate 0 to 0.5 of this part. So that's why it's good to do a variety of problems, change it up. So you could say, okay, how does changing something change the integral? Then you become proficient at it. So you see the x disappears. You just have 1. And that's it. So now, becomes, is that bigger? So the other integral came out 1.19. Yeah, it's actually bigger now. 6.51275,799. So I've got everything else ready. I've got 2 and the pi, the k, the x. Okay, but now I don't know what the alpha is. So what does the alpha need to be so that the plate has the same charge that we want? So then I'm going to do dq is equal to sigma dA. dq is equal to alpha 1 over r. What's dA? 2 pi r dr. From 0 to big R, okay? And so I'm trying to find out what alpha needs to be. So this is equal to q. Okay, then alpha, 2 pi alpha comes out of the integral, and then integral 0 to r. Well, if r cancels the r, it's just integral dr. Okay, then what's that? Integral dr is just r. And then 0 to r is just r. So literally it's just 2 pi alpha r evaluated from 0 to r. It's just 2 pi alpha r. Okay, so then alpha needs to be q over 2 pi r for it to work out. So again, it's a fudge factor. Okay, now I can integrate the whole, I can multiply out the whole thing. Okay, here we go. Okay, so 6 point, let's do it here. 6.51275,799 times 0.354 times 9. Forget the 10 to the 9th, it's going to cancel. Times 2 times pi. Okay, 130. Then multiply that by alpha, right? Multiply that by alpha. So then alpha is q. So q is 10 nanocoulombs. So that'll be multiplying it by 10 divided by 2 divided by pi divided by the radius, which was 0.5. Let's see. 414.99. So the electric field is 414.99. Now compare that to the electrical field of a uniform plate at that same distance. What was that? 414. 303. Oh, right there. Oh, quite bigger. 414. Wow. About 100 larger. So it kills the ring, of course, and it kills the uniform plate. Yeah, so obviously there's a lot more charge in the center now in this case. Whew. Good, huh? Everything is checked by logic. Everything is double checked. See if it makes sense.